So what is a line integral? Well, in Calculus 1 we learned to integrate expressions like this one, right? So, you know, an integral from a to b of f of x dx, and what it was the area under the graph of f of x, or maybe the area between the x-axis and the graph of f of x on the integral from a to b dx. And multiple integrals we did this semester, as a matter of fact. That's Unit 4, where we integrate twice some function of two variables, x and y, and we integrate with respect to one of the variables first and then the other variable second, and our limits of integration usually describe the region R that we're finding, and what we really find when we do this are the area under this surface and above this region R, whatever that region R may be. This section we're going to do something different, a new type of integral called a line integral, and look at some of the applications of line integrals, and they're notated like this. We got a curve f of x, y, z ds, questionable what the ds is going to be, and some curve c is what the integral is about. By the way, that's the three variable interpretation, and this could also be just f of x, y if it's a line integral in two-dimensional space. So it takes place over an interval or a plane region, but over a piecewise smooth curve C. Recall the difficulty we had in parametrizing this smooth curve C, and that's going to be the difficult part of this type of thing. Consider the mass of a wire of finite length given by some curve C in space, and suppose the density is not constant, but it's x, y, z, or the density at the point x, y, z is some function of x, y, and z. We partition the curve C into subarcs by inserting P0, P1, all these points that make the curve chopped up into itsy-bitsy pieces along the wire, and we let the length of the ith subarc be called del S, or delta S. And we choose a point in each subarc to represent the density of the wire on the entire subarc, with the density being f of x, I, y, I, z, I, x, I, y, I, z, I being the point that we choose in the ith arc. So the mass of the wire can be approximated by this, okay? It would be the sum, I going from 1 to n, of our f of x, I, y, I, z, I times delta si, which would be the length of that arc. So we're assuming a constant density over that entire small piece of arc. And if we let del be the norm of the partition, represent the length of the longest subarc, then the limit of this sum as that del approaches 0 is the mass of the wire. So we will define line integral in 2D and 3D. A two-dimensional line integral over some curve CS, smooth curve in the xy plane, of f of xy ds is a limit as the del goes to 0, I goes from 1 to n, of f of xi, yi del s. That's for the plane. And in three-dimensional space, the limit as limit over a space curve of our f of xyz ds is a limit as our del goes to 0, I going from 1 to n, of our value of the function at a point in that curve times del si, that's it, in space, provided that that limit exists. And how do we evaluate such an integral? Find out in the next video.